Section 1. By the dark opening of 1942, the Allies faced a terrifying variable in the calculus of survival. For every new cargo ship launched from a slipway, 2 were being torpedoed in the North Atlantic. The United Kingdom, an island nation that required 1 million tons of imported material every week merely to survive, was bleeding out. The German High Command had identified a fatal logistical vulnerability. Realizing that they did not need to invade England to win the war, they simply needed to cut the supply line long enough for the island's reserves to hit zero. Now, let's open the operational records and analyze the systems that defined this campaign. To understand the gravity of the crisis, we must look at the conflict through the lens of Admiral Karl Dönitz, the commander of the German U-boat fleet. He conceptualized the battle not as a series of naval engagements, but as a Tonnage a tonnage war. This was economic warfare distilled into a ruthless mathematical formula. Dönitz calculated that if his U-boats could sink an average of 700,000 gross registered tons of shipping per month, the British logistics system would collapse before American industrial might could fully mobilize. The target was not the escorting destroyers or the battleships. The target was the cargo capacity itself. When we analyze the operational data from this period, we see that the Tonnage War was fundamentally a battle of rates, the rate of destruction versus the rate of production. In the early years of the war, the rate of destruction was winning by a landslide. The wolf packs, groups of U-boats coordinating attacks on convoys, were decimating the merchant marine. But the problem was not just the efficacy of the German torpedo. It was the lethargy of Allied shipbuilding. Britain's maritime industry, while storied and skilled, was built on tradition rather than speed. Ships were constructed individually, almost like artisanal projects, designed for longevity and specific trade routes. The hulls were riveted plate by plate, a labor-intensive process requiring highly specialized workers who were in short supply. A single merchant vessel could take 6 to 8 months to complete. In a peacetime economy, this craftsmanship was a mark of quality. In a tonnage war, it was a liability. The strategic dilemma was stark. The Allies were attempting to fight a high-velocity war of attrition with a low-velocity industrial base. The logistical demand of the war in Europe, fuel, ammunition, food, and raw materials, was skyrocketing. Yet the pipe delivering these goods was shrinking with every sinking. The Atlantic Ocean had become a graveyard for British logistics, and the shipyards, operating on obsolete methodologies, were powerless to close the gap. The system was failing. Unless the Allies could fundamentally alter the variables of production, the tonnage war would be lost, not by a lack of courage, but by a lack of capacity. Section 2. The operational reality in 1940 presented the Allies with a seemingly impossible equation. Britain needed ships immediately, but the established shipyards in both the UK and the United States were already at maximum capacity constructing warships for the Navy. The logistical infrastructure simply did not have the bandwidth to absorb a massive merchant marine program. To solve this, the British merchant shipbuilding mission arrived in the United States with a blueprint for a simple, coal-burning tramp steamer known as the Ocean class. Their plan was to contract existing heavy industries to build these vessels, but they quickly hit a wall. Every dry dock with the requisite skilled labor was already booked solid. This deadlock forced a radical pivot in industrial strategy. The plan could no longer rely on finding shipbuilders. It had to rely on finding systems managers who could learn to build ships. This search led to Henry Kaiser, an industrialist with zero experience in naval architecture but a profound mastery of complex logistics from building dams and highways. Kaiser looked at a ship and didn't see a nautical vessel. He saw a large steel structure that could be standardized. The plan shifted from a maritime project to a mass manufacturing one. When we analyze Kaiser's approach, we see a complete rejection of the naval status quo. Traditional shipbuilding was a linear process. A keel was laid, and the ship was built up piece by piece from the bottom, causing the slipway to be occupied for months. This was the primary bottleneck. Kaiser's plan proposed prefabrication on a massive scale. Instead of building the ship in the slipway, the plan called for building sections of the ship, bows, deck houses, midsections, in scattered factories across the country, then transporting them to the yard for final assembly. Crucially, the plan demanded a transition from riveting to welding. This was a decision driven purely by labor logistics. Riveting was an art form requiring years of apprenticeship. Welding was a mechanical skill that could be taught to a farmhand or a housewife in a few weeks. By replacing rivets with welds, the plan unlocked a vast, untapped labor pool, including women, who would soon dominate the workforce, effectively bypassing the shortage of specialized male workers. However, the naval establishment viewed this plan with deep skepticism. They argued that welded ships would be brittle in the freezing North Atlantic, and that mass-produced vessels would lack the reliability required for convoy duty. The operational risk was high. The Allies were betting their entire supply chain on an unproven industrial methodology and a shipyard workforce that had never seen the ocean. Yet, the strategic context left no alternative. The goal was no longer to build the perfect ship. It was to build a sufficient ship faster than a torpedo could destroy it. The blueprint was finalized. The yards in Richmond, California, and Portland, Oregon were graded, and the order was given to commence the largest single class of ship construction in history. The logistics of the war were about to shift from a craft-based economy to an assembly line juggernaut. Section 3. The instrument chosen to fight this industrial war was officially designated the EC-2SC-1, but history remembers it as the Liberty ship. To the naval purists of the 1940s, it was an aesthetic and technological regression. President Roosevelt famously referred to it as a dreadful-looking object, and Time magazine dubbed it the ugly duckling. However, when we strip away the aesthetics and analyze the vessel purely as a logistical enabler, we find a masterpiece of systems engineering. The Liberty ship was not designed to be fast, nor was it designed to be durable in the traditional sense. It was designed to be produced. The genius of the Liberty ship lay in its ruthless adherence to standardization. In previous eras, a ship's components were often bespoke, tailored to the specific hull sitting on the slipway. The Liberty program inverted this logic. It utilized a single, immutable design that was distributed to shipyards across the United States. This meant that a rudder built in a factory in Ohio would fit perfectly onto a stern section constructed in Portland, Maine, or Richmond, California. The enabler here was not the steel itself, but the interoperability of the parts. This shattered the regional bottlenecks that had plagued British shipbuilding. The entire American industrial base, from Denver to Detroit, could now act as a single distributed shipyard. When we look under the hood, the systems analysis becomes even more revealing regarding supply chain constraints. The designers made a critical decision regarding propulsion. The modern standard for merchant vessels was the steam turbine, which was efficient and fast. However, manufacturing the precision reduction gears required for turbines was a highly specialized process with limited capacity, a massive bottleneck reserved for high-priority Navy warships. Recognizing this, the Liberty designers opted for an obsolete 19th century technology, the triple expansion steam reciprocating engine. To a naval architect, this was a step backward. But to a logistics planner, it was a stroke of brilliance. The triple expansion engine was heavy, tall, and inefficient, but it was simple to manufacture. Any foundry that could cast parts for locomotives or mining pumps could build one. By choosing inferior technology, the Allies bypassed the critical shortage of precision gearing, ensuring that the propulsion supply chain could keep pace with the hull construction. The system prioritized availability over performance. The most revolutionary aspect of the Liberty ship, however, was its modular construction method. As we established, Kaiser's yards utilized prefabrication, but the scale of this logistical shift is difficult to overstate. We must visualize the shipyard not as a construction site, but as a final assembly plant. The ship was broken down into manageable subassemblies, bow sections, double-bottom tanks, deck houses, weighing up to 50 or 100 tons. These sections were built in prefab yards, often miles away from the water, where workers had room to operate and cranes could move freely. This approach decoupled the construction process from the limited resource of the slipway. A keel was laid, and giant sections were lifted into place and welded together like a massive steel jigsaw puzzle. This method drastically reduced the logistical footprint of each vessel on the precious waterfront real estate. The shift from riveting to welding also had a secondary logistical benefit beyond labor speed: weight reduction. Riveted ships require overlapping steel plates to hold a seal. Welded ships join flush. This saved approximately 200 tons of steel per ship, steel that was desperately needed for tanks and artillery. Furthermore, a lighter ship meant a higher payload. Each Liberty ship could carry over 10,000 tons of cargo. To put that lift capacity into perspective, a single Liberty ship could carry 2,140 jeeps, 440 light tanks, or 230 million rounds of rifle ammunition. This was the ultimate enabler. The Liberty ship was a disposable container, a logistical munition fired across the Atlantic. It was slow, plodding at 11 knots, making it a sitting duck for U-boats if caught alone. But its defense was its reproducibility. It transformed the convoy system from a defensive measure into a relentless conveyor belt. The sheer volume of cargo these ships could move meant that even if the enemy sank a percentage of the fleet, the net amount of supplies arriving in Liverpool or Murmansk would still be sufficient to sustain the war effort. The Liberty ship proved that in a war of systems, a perfect ship that arrives next year is useless, but an ugly ship that arrives today is decisive. Section 4. When we perform a systems autopsy on the Battle of the Atlantic, we must place two critical graphs side by side. On the left, we have the kill rate of the German U-boat fleet. On the right, the launch rate of American shipyards. For the first half of 1942, the data paints a catastrophic picture for the Allies. The U-boats were operating with lethal efficiency during the Second Happy Time, sinking merchant vessels faster than the combined industrial might of the US and UK could replace them. In June 1942 alone, Axis submarines sent over 800,000 tons of shipping to the bottom. At that specific operational tempo, the Allied logistical model was mathematically doomed to approach zero. The burn rate of tonnage was simply unsustainable. However, a systems analysis of the American shipyards reveals a phenomenon known as the industrial learning curve. In the early days of the Liberty program, the cycle time, the duration from laying the keel to delivering the ship, was approximately 244 days. This was too slow. But Kaiser's system was designed to optimize itself recursively. As workers mastered their specific welds and logistical bottlenecks in the supply of prefabricated sections were cleared, that number began to freefall. By late 1942, the average build time had collapsed from 8 months to just 42 days. This is where the logistical autopsy reveals the turning point. The system had achieved a velocity that defied historical precedent. We are not just seeing an increase in capacity, we are seeing a compression of time. The shipyards were effectively manufacturing time itself, buying the Allies the operational breathing room they desperately needed. To demonstrate the sheer elasticity of this system, we must look at a specific event that took place in November 1942 at the Richmond Shipyards in California. It was a planned stress test of the logistical chain, centered on hull number 440, the SS Robert E. Peary. Kaiser wanted to prove that the constraints on shipbuilding were purely mental, not physical. The clock started at 12:01 a.m. on a Sunday. Teams of welders swarmed the slipway. Because the prefabrication system was fully primed, 250-ton sections were ready and waiting. In the first shift, the bottom shell was laid. By the end of the first day, the ship was taking shape. The assembly process was so rapid that the paint was literally drying on the bow while the stern was still being welded. 4 days, 15 hours, and 29 minutes after the keel was laid, the SS Robert E. Peary was launched. While the Peary was a publicity stunt and not the standard run rate, it signaled a terrifying reality for the German high command. The American system had unlimited scalability. The bottleneck had been completely blown open. Now, let's map this industrial velocity against the German strategic model. Admiral Dönitz had built his entire war plan on a static assumption: that Allied shipping capacity was a finite resource that could be depleted. He had not factored in a variable where the enemy could regenerate assets faster than his forces could destroy them. By 1943, the Tonnage War equation had inverted. When we analyze the data from 1943, we see the crossover point. The U.S. maritime industry was launching 3 Liberty ships every single day. In the time it took a German U-boat to leave its base in Lorient, transit to the hunting grounds, hunt for 2 weeks, and return to port, a cycle of roughly 1 month, American shipyards had launched nearly 90 new merchant vessels. The wolf packs were no longer hunting a dwindling herd. They were facing a hydra. For every ship they torpedoed, the industrial machine produced 2 more. The psychological impact on the U-boat crews was devastating. They were reporting successful sinkings, yet the convoys were getting larger, not smaller. The demand for destruction created by the U-boats was high, but the capacity of American industry had become effectively infinite relative to the threat. The systems autopsy confirms that the German defeat was not solely tactical. Yes, the Allies introduced better radar, long-range aircraft, and code breaking, which spiked the U-boat mortality rate. But even before those tactical victories took full effect, the logistical war had already been decided on the slipways. The German industrial base, struggling to build just 20 to 30 U-boats a month, was pitted against an American system churning out millions of tons of shipping. The sheer mass of the Liberty program acted as a logistical shield. By flooding the Atlantic with targets, the Allies saturated the German offensive capacity. The U-boats simply ran out of torpedoes before the Allies ran out of ships. The data shows that by the end of the war, the United States had built over 2,700 Liberty ships. The system had not just survived the attrition, it had overwhelmed the attritional force through the brute force of mass production. The shipyard problem had been solved not by elegance, but by velocity. Section 5. The final verdict on the Battle of the Atlantic challenges our traditional understanding of military victory. While we often laud the courage of the convoy escorts and the technological breakthroughs in sonar and code breaking, the foundational truth is that the Allies won because they successfully shifted the conflict from a naval engagement to an industrial one. The German Tonnage War failed not because their U-boats stopped sinking ships. They remained dangerous until the final days, but because the Allies rendered the sinking rate irrelevant. When we distill this campaign down to its logistical essence, we find a triumph of sufficiency over perfection. The Liberty ship was, by traditional naval standards, a mediocre vessel. It was slow, prone to hull fractures in cold water, and equipped with antiquated engines. Yet, as a system, it was flawless. The Allied planners understood a critical principle of high-stakes logistics. In a crisis of attrition, quantity has a quality all its own. They realized that a supply chain relying on high-performance, complex assets is fragile, whereas a supply chain built on redundant, standardized, and rapidly replaceable assets is anti-fragile. The strategic lesson here is the power of design for manufacturability. The decision to prioritize the triple expansion engine over the steam turbine is the defining moment of the campaign. A purely tactical analysis would have demanded the faster turbine to outrun submarines. But a logistical analysis recognized that the supply chain for turbines was the bottleneck. By accepting a suboptimal technical solution that was widely available, the Allies ensured the velocity of the entire system remained high. They accepted a tactical vulnerability to secure a strategic inevitability. Germany, by contrast, remained trapped in a mindset of craft production and tactical optimization. Their engineering was superb, but their industrial systems lacked the elasticity to recover from losses. They were fighting a war of finite numbers against a system of infinite regeneration. The Liberty program demonstrated that the ultimate weapon in modern warfare is not a specific piece of technology, but the capacity of the industrial base to sustain operations under extreme pressure. The shipyards didn't just build ships, they built strategic depth. Ultimately, the Liberty ship serves as a timeless case study in the trade-off between efficiency and resilience. In our modern era of just-in-time supply chains and hyper-optimized logistics, the lesson of the Liberty ship is a stark warning. Optimization works in a predictable environment, but in the chaos of conflict, redundancy and simplicity are the only things that ensure survival. The Allies survived the darkest period of the Naval War because they built a system that could absorb failure and keep moving. As we close the operational records on the Liberty ship, we are left with a profound realization about the nature of conflict. We tend to focus on the spear's tip, the combatants, and the tactics, but the outcome is often decided by the invisible hands casting the shaft. The Liberty ship teaches us that in the face of an existential threat, the most sophisticated solution is often the one that simply works again and again. Victory, it turns out, is a product of the assembly line.